Okay, and this I'm gonna cover a lot. I'll try to explain it to the best of my ability. Today is April Fool's Day, 2016. Thermal expansion. When you have a hot young star, they're gonna be really hot, really big, really bright. And for the most part, what you get is when they cool down, they contract. That's what stars do. They contract when they cool down. Now, I'm not saying it's purely because of thermal contraction, because there's a lot of mass loss, but that's a general rule of thumb. And I have here, all gases, liquids, and solids have some contraction and expansion effects with regard to how great of a temperature is made. Change in temperature is made. That delta means change. When you see that little triangle, looks like a little spaceship, that means change in. So 1 plus 2 equals 3. The change in 3 to, say, 2 plus 5 equals 7. The change in 3 to 7 would be 4. It's pretty simple. But also go on, negative. So if you have negative 1 plus 2 is 1. And you can do, negative change as well. Actually, no, I don't think, I think this is like absolute value. I think I remember that. Even if you have absolute value of 4, it still means 4. But anyways, as a general rule of thumb, gases contract, expand by much larger amounts than do liquids and solids, and then solids expand and contract less than liquids. Contraction and or expansion is dependent on molecular motion. This is the big part I wanted the people to understand. If you have a gas, the degrees of freedom are a lot greater. You have translational, you have rotational, and you have translational, rotational. There's another one. I can't remember what it was. I should have wrote that down. But anyways, the molecules can move wherever they want very freely and really rapidly. So when you cool them down, they contract a hell of a lot more per unit volume than would, say, a liquid. So I wrote here, gases are much less dense than our solids and liquids, so they have much greater degrees of freedom. They can expand and contract a lot more. And that has a big part when gas giants are really big and they become really, really small. As well, you have mass loss in there too. Liquids, they sort of slide past each other like these little, looks like some type of cell. I'm not going to mention what type of cell that looks like. Liquids slide past one another but can't move freely as gases. They have limited motion. They can't, go this way or this way. And a lot of times maybe they just spin around on their axis too. That's rotational motion. With solids, the expansion and contraction is very, very limited. They have very limited intermolecular motion because, they form the crystalline structure. The bonds between them are really, really strong. Okay, so the more bonds you have made as the star cools and collapses and the chemicals combine with one another in synthesis reactions, the material, it can't move freely, so it just stays put. Of course, this isn't a good rule of thumb for ice, because ice obviously expands when it cools, but that's an exception to the rule. Water is really weird like that. But I have here written, solids intermolecular motion is limited, so it contracts, expands only when there are larger temperature differences. So it takes a lot more to make a solid contract a tiny bit or expand a tiny bit than it does, say, a gas. And you can do a little experiment with this. Go into a hot area with a 2-liter bottle or a thing of empty jug of milk. Obviously you have drinking the milk already, but let the air get inside the milk jug. And what you do, this is a pretty crappy 2-liter bottle. What you do is you put the hot air in there, and then you stick it, you close the cap on, and you stick it in the refrigerator or the freezer, and it will contract by great amounts. But if you were to do the same thing with like a piece of metal, it wouldn't contract nearly as much as that 2-liter bottle would. Further, here's another set of ideas. April Fool's Day. You have, okay, this is about the Herndon's whole Earth decompression idea, but this is basically what it's going over. You have a large gas giant, and it's lots of pressure. It squeezes that internal structure in there really like great amounts because the atmosphere is really thick, it's really really heavy, and it's very hot. Okay, and as the atmosphere is ripped away from getting too close to a hot host star, then the inwards material, this will start pushing out slightly. Okay, because the atmosphere is being released. And what happens is some pressure is released and the inner object will expand slightly, from the release of that atmosphere. So it will expand slightly and it will allow itself to release that heat a little bit more effectively. And over time, as that thick atmosphere is ripped away, some more pressure is released and the inner object expands even more. So you have an object just ballooning out, but in very small amounts because it's mostly solid. It's not gaseous in there, and it is a little bit more liquid than it is gaseous, let's put it that way. And then you have the remaining pressure released as the rest of the atmosphere is dissipated, and the inner object will begin cooling and contracting again because it can start cooling down, and that's where the thermal contraction takes place. When it cools down, it starts to shrink because the intermolecular motion is diminishing considerably. And I have here the inner object begins cooling and contracting again, and this is 3D. Imagine this is three-dimensional. And what I have here is you have one giant plate with vents called volcanoes, the ring of fire, oceanic ridges, etc. And all that heat comes out of that solid body in the form of liquid material called magma, and the entire shell contracts. And this is important because when an entire shell contracts like that, this is the pre-final contraction. It's kind of smooth, and as it contracts, it forms these ridges. And depending on what material is present and how well it resists that motion of that plate falling inwards, I should say the entire shell will determine if mountains form in that region. That's why mountains form, and that's why you have huge folds in land. Okay, you have huge folds of material on the surface. Okay, that's why there's folds in the crust, and that's why there are mountain ranges, because the whole thing is contracting. It's not because two plates are moving and bashing into each other. The whole Earth. That's why it's called whole Earth decompression dynamics. It was decompressing when the atmosphere was moved, but then it's recontracting again, forming mountains. But that's pretty simple to understand. If anybody has any questions concerning that, Baz Taylor, if you want to ask me any clarifying questions concerning it, go ahead. Or if you need me to overview something in specific, I'll be more than willing to help out. All right, later.